He is the Faculty Chair in Earthquake Engineering Excellence at UC Berkeley. He is a registered professional civil engineer and has authored more than 450 research publications, primarily in geotechnical earthquake engineering. He created and led the Geotechnical Extreme Events Reconnaissance, GEER, Association. He is a member of the U.S. National Academy of Engineering and has received the Seed Medal, Terzaghi Award, Ishihara Lecture, Peck Award, and Joyner Lecture. He also had the pleasure of teaching me about 20 years ago.
That's the key to life, is to be old and to have great students who have learned something from you. But they already came smart, and they just continue to get smart. I'm going to talk about the selection of a seismic coefficient in a pseudostatic slope stability analysis for a tailings dam. And this work is with Professor Macedo at Georgia Tech. When we think about the complexity of an earthquake loading, as shown with that acceleration time history, the intensity is changing constantly during the ground shaking. There's frequency content, there's duration. It is remarkable to think that we can simplify that by having a seismic coefficient acting on the weight and moving the material in one direction to replicate that sophisticated complex loading. But if we look at the combination of the seismic coefficient, the strengths, and the calculated factor of safety, if we select an appropriate combination of those parameters that get the same answer, they're calibrated against more advanced analysis like, well, case history is number one because we learned from the field, but also more advanced analysis, then this can be a useful screening analysis, preliminary analysis. It can give you insight into allowing you to say, this dam has an issue, this dam probably doesn't have an issue. Now, selection of a seismic coefficient had largely been done through precedence. Seismic coefficients of 0.1 to 0.2. And then a range of different factors of safety we're using. And so, for example, in New Zealand, the Aviemore Dam, using a factor of safety of 1.5, you go a little further down to Digma Dam in Chile, and same seismic coefficient, it's 1.15. So it's not just the seismic coefficient. You have to put that in combination with the factor of safety to get an equivalent level of performance. Probably the most famous pseudostatic analysis was during H. Bolton Seed's ranking lecture, where he proposed that if you use a seismic coefficient of 0.15 and appropriate dynamic strengths, and you calculate a factor of safety greater than 1.15, you will have shown that that dam will perform appropriately. He caveated that by saying these are for well-built water dams, water retention dams, and he considered 1 meter of movement as being acceptable. What about other levels of movement? Many of our tailings facilities can withstand maybe 2 or 3 meters of displacement. Why should K be 0.15 around the globe? I've worked on a dam next to the San Andreas Fault, which can generate a magnitude 8 earthquake, and I've worked on a nuclear facility where the nearest major faults were over 200 kilometers away. Why would I use exactly the same seismic demand coefficient, 0.15, throughout the world? There are other methods, as shown here. For example, Mary Ellen Hines and Gus Franklin, they're working the Corps of Engineers. They have to sort through all their catalog of dams to come up with a way of screening of which ones they should focus on. And so they came up with a seismic coefficient that was about half of the PGA on rock. Very important, they actually assumed 3 times amplification. Now, if the ground motion is 0.1 G, maybe you get that kind of amplification. But if the ground motion's 1 G, because of nonlinearity, you're not going to get that level of amplification. And the displacement was calibrated to 1 meter. I've worked in South America and often seen people use Sarragoni in 1993. That's a seismic coefficient, let's say it's 0.2 of the PGA raised to the 1/3 power for higher PGA values. That's based on observations of port facilities that are rigid, undergoing liquefaction beneath their base and moving. A tailings dam that is 100 meters high is not a rigid system. So, seismic coefficient. It should depend on the level of shaking. I think there's no debate about that. Therefore, at different distances from the fault, different earthquake magnitudes, and also the dynamic response of what's shaking, because it is a non-rigid system. And it should depend on the criticality of the structure, which really means the acceptable level of seismic performance. And how do we evaluate that? Whether it's a FLAC analysis or I maintain a pseudostatic analysis, it's done through a selection of an allowable seismic slope displacement. So let's select a rational, displacement-compatible seismic coefficient that gets us the same answer or conclusion that we would have gotten if we did a seismic slope displacement procedure. The Brahim-Macedo 2019 slope displacement procedure is one of the procedures that's out there. There's other procedures we have for subduction zone, models that looked at a range of different yield accelerations and periods of sliding masses over 6,000 ground motions, looked at validated against case histories. Jorge Macedo, when he was a young man, did nearly 3 million analyses to be able to populate the space so that we could develop a regression analysis that we felt comfortable with. A couple of things I want to point out is we decided to use the design acceleration response spectrum as the seismic demand. Peak ground acceleration would only matter if the system sliding was rigid. It is not. And just like structural engineers use spectral acceleration at 1 second for a 10-story building, not PGA, we as geotechnical engineers, if we're looking at a system sliding, we should be looking at the spectral acceleration at the period of the sliding mass. The other important thing is if it's a rigid block sliding, you can do the Newmark analysis. The late Professor Harry Seed with seismic DC realized there is a dynamic response of whatever shaking. It's flexible, it's not rigid. So they did what is called a decoupled approximation. They calculated the dynamic response using a program that had continuity of displacement. So there's no slip. And then they used that response characteristic to calculate how much slip you'd get. That's clearly an approximation, and we can do better now. In fact, Ellen Rathje with myself developed essentially the dynamic response and sliding response all occurring at the same time and being able to get those episodes of slip, which changes the dynamic response characteristics of the sliding system. And this is a comparison that shows sometimes the numbers are small and it doesn't matter how you do it. There are some times where the decoupled approximation is conservative, but how conservative is it? There are some times where the coupled analysis actually calculates larger displacement. So you're not always conservative when you do a decoupled analysis. So we end up with a plot that looks like a lot of the plots that you've seen in terms of the log of seismic slope displacement versus KY. Here's at 1 ground motion intensity level for different magnitudes. In the end, we have a spreadsheet that allows you to calculate a slope displacement as a function of these parameters. I put this equation in here for Christina. She loves equations. But the whole idea is it's a function of a number of things. Why not just invert the problem and solve for the displacement, solve for the seismic coefficient that's compatible with what you say is the allowable level of displacement. Make that an input parameter as opposed to a solution. And then bring in intensity to the ground motion. The K value, you don't need to worry and memorize these equations because it's all in the spreadsheet. Very important thing, we wrestled with the fact that what should be the lowest value, and we feel that because of the simplifications and limitations of the method, you should never use a seismic coefficient less than 0.03. So we wanted to set a base limit. Let's look at one of the plots that's in the paper where we have seismic coefficient for one case. We have a dam with a fundamental period of 0.3 seconds, and we're looking at the seismic coefficient versus spectral acceleration at the degraded period of the sliding mass, 1.3 TS. If we just look at the case where the allowable displacement is 100 centimeters, magnitude is 8, the red line, it makes sense that as the intensity of the ground motion increases, the K that you use has to increase as well. But let's pick one intensity level. Spectral acceleration is equal to 1g. If the allowable displacement is 30 centimeters, you use a seismic coefficient of 0.28. That's a pretty stringent thing to keep the displacement under that loading to 30 centimeters or less. So to ensure you get a consistent answer, you have to use a pseudostatic coefficient that's equal to 0.28. If you can allow more deformation, then you can use a seismic coefficient of 0.13. If you use that seismic coefficient of 0.13, then you're essentially tying that to being 1 meter of acceptable displacement. That's for a magnitude 8. This is for a magnitude 7. It makes sense. A magnitude 7 has fewer cycles of loading, so to get the same performance, which is what we're shooting for, use a lower seismic coefficient, 0.08. I want to emphasize that the Newmark calculation I'm talking about now is a shear displacement, which is slip along a failure plane, as well as distributed deformation through the sliding mass because it's not rigid. If you have a sandy or gravelly or material like that that can actually undergo volumetrically induced deformation, you should add that in. To keep things straightforward, we found that when you get severe loadings and high shear, the volumetric is on order 20% of the total displacement. So here's the proposed procedure that's in the paper. You always start with, are there materials in the system or the foundation that can lose significant strength? And you use post-shaking reduced strengths and do a pseudostatic, or you do a static stability analysis, and you make sure that the post factor of safety is greater than 1.1, and use compatible strengths. Then you make the tough decision as an engineer with the owner and the reviewer, what is the allowable amount of displacement? And for this procedure, because it's simplified, do not use it with more than 3 to 4 meters of displacement, because we're really pushing this method beyond that. And we're going to use a slope displacement that's 80% of the allowable displacement. And because we want to be reasonably conservative, we're going to use the 16th percentile exceedance level, or epsilon equal to the standard deviation. We have to estimate the initial period of the sliding mass. It's 4h over vs. If it was level ground, a very large flat slope, that would be appropriate. If it's a triangular system as shown here, it's 2.6h over vs. And everything else in 2D is between those two. And so you can actually go through a weighting procedure that we talk about in one of the reference papers to find out whether it's closer to 4h over vs or closer to 2.6h over vs, whether you should be using 3.3h over vs. So you have that period. Then you characterize the seismic demand below the sliding mass, just like you would do for a base shear on a building, and you get your spectral acceleration at the degraded period and your magnitude. And then you calculate your displacement compatible seismic coefficient as a function of those input parameters. If you perform a pseudostatic slope stability analysis with that displacement compatible seismic coefficient, and the factor of safety is greater or equal to 1, then the D shear, or the displacement from shear-induced deformation that you would have calculated would be less than what you said was allowable at the selected level of displacement, and therefore your total D will be less than D allowable. So let's go to a tailings dam. All of this was pulled from the literature, so this is from Venezuela 2015, as well as a follow-on study. It was shaken by the 2010 Mali earthquake. No materials lost severe strength loss, and the post-seismic factor of safety was greater than 1.1. We used the strength values from their papers. There was no significant deformation observed. So normally you're doing a forward analysis and you're talking about a meter or 2 or 3 as being acceptable. Here we're trying to do a back analysis to see how well it works. So we're saying, okay, they said there was no displacement. No is a pretty limiting number. So we're saying negligible, let's say it's less than 5 centimeters. And therefore the shear displacement had to be less than 4 centimeters. We estimate the period of the sliding mass, 2.6 h over vs, because if you squint, this looks a little bit like a triangle. And so we get 0.5 seconds for the period of the sliding mass. We estimate the seismic loading that's provided from this paper as 0.18 G for this earthquake, so this is obviously a low level of shaking. We then apply a displacement compatible K of 0.12, which is from the spreadsheet, from the calculations directly with these inputs. We put that into a pseudostatic slope stability analysis, calculate a factor of safety of 1.8, which is in excess of 1. Therefore, the method says that the displacements are going to be well less than 5 centimeters, which is consistent with the observations. So we evaluate dam performance at every level in terms of seismic slope displacement. So if we're going to use a pseudostatic method, it should be calibrated using a displacement-compatible seismic coefficient to evaluate performance. K should depend on the earthquake loading, but K should also depend on what you consider to be the allowable level of displacement. It should be a displacement-compatible seismic coefficient. If that pseudostatic slope stability analysis done with that displacement-compatible K has a factor of safety greater than 1, it's calibrated to ensure that the actual D that you would have calculated is less than what you consider to be allowable. Now, you should advance to estimating the seismic slope displacement directly, and you should use the Bray and Macedo 2019 procedure for shallow crust earthquakes, Macedo et al. 2023 for subduction zones. You should move to FLAC analysis because you gain great insight, but this is a great way of starting things. And then also, even if you do a FLAC analysis, which is high speed, make sure you include the post-liquefaction volumetric settlement because it's there, and most of our models are shear-based, and they don't capture that. Thank you.
All right, first question.
Thank you, Dr. Bray. I have 2 quick questions. So first of all, the Chile earthquake case, is that, what type of earthquake? Is that subduction zone?
That was a subduction zone interface earthquake. So we used Macedo et al. 2023 to calculate that K.
Okay, that makes sense then. Then the second question, in industry base, we are focusing on this horizontal deformation, but the dam height varies a lot, and then the performance of the cores, and then it all depends on the strain potential inside. What are the thoughts on accommodate this deformation to the actual performance of the structure?
That's a very good point because you have components within the system, so it really comes down to the most difficult thing to do in this method. It's this step. What is the allowable level of displacement? Okay, when I first presented this to one of my former students, they go, "Great, Professor Bray, now you have made my life very difficult," because that's the hardest thing. I can get the seismic loading, I can do static analysis, but deciding how much deformation is acceptable is a really difficult thing to do. But I think it gets to the heart of what you're talking about, is if I've got filter zones, if I've got zones, how much displacement will lead to an offset of something where it could compromise the performance of the system? But you're focusing on performance. And I think that if you have a downstream dam that's really robust, I think this method gives you displacement and it correlates really well to performance. If you have a more intricate design and you've got something that has different layers and you're worried about strain, you have to move to a FLAC or a finite element type of analysis and look at differentiations of strain. But I would never trust a FLAC analysis until I'd already done a pseudostatic analysis or a slope displacement analysis to have an idea what the answer is, because you can get some very wild answers, and at least this method has been calibrated against case histories. And in the end, if it gets the right answer by having compensating errors, then it's a useful tool. And so the pseudostatic method is not the best place to stop most of the time, but it's a great place to start. And it's controlled by, it's required by some regulators in some countries, so you might as well start where they're requiring you to do it, but do it smartly.
All right, next question.
Hi, thank you for the presentation. My question is, what is your opinion on fixing the critical slip to be the same as the critical slip during static loading. I've seen differing opinions on that.
Oh, that's a very, when you go forward and you're doing, let's say, a seismic slope displacement analysis, you have to pick a failure plane to calculate your yield coefficient as one of the inputs to calculate displacement. Don't just pick the one that has the lowest static factor of safety. Don't just pick the one that has the lowest yield coefficient, KY. It's a dynamic problem. So you're doing a static analysis to calculate a dynamic resistance of KY. You have to remember it's a dynamic problem. Things are shaking, and all things being the same, things tend to get amplified through a mass, and so you have to think at the top. So you want to use multiple failure planes and calculate multiple KYs so that you can explore that space. That's a very good question.
Does that mean moving the shear surface back into?
Yes.
Further into
Yeah. So, yeah, don't just take the surface that has the lowest static factor of safety, move it around and play with it, and really make sure that you're exploring possibilities, because as the mass gets bigger, then the lower KY value will come up and you can actually get more displacement. But as the loading gets higher, and the loading tends to get higher as you get a little bit toward the top, that can flip it around. So it really is KY over Kmax that matters. KY is the dynamic resistance, Kmax is the maximum loading.
All right, and that's all the time we have for questions.